you earlier in the semester about composite functions. And at that time, I tried to build a case for the fact that we use composite functions a lot in everyday life. The idea of a composite function is that we have a chain of events, more or less. If I think of having two events, the first one has to happen before the second one does. The first one has an input resulting in an output. The second one starts with the output of the second one, or the first one, and has its own then conclusion. And if we look around the room, I can see you all used it appropriately in a personal way, because I don't see any socks over your shoes. Okay, so the first action is getting, well, I hope I don't see any socks over shoes. The first one is getting a pair of socks out, and the output is socks are on my feet. And then the second function or action is that I'm going to have shoes, and so the second action starts with the socks on my feet, and then ends with shoes on my feet. And so we can't do the second without having the first. Same thing happens with our mathematical composite functions. If we look at functions f of x and g of x, and I say I want you to build a composite function of those, and we're going to call the result h of x, what would be our way of expressing a composite using f of x and g of x? And there's two ways you can do that. Well, what if we start with g of x? That's going to be our first function. And once we're done with that, so g of x is the output of g of x, of the function g. But I'm going to use that now as a starting point in function f. So now g of x is not the output of function g, it's now, how would you describe that? As we see it here, g of x is the input. Well, it would be the input of function f as we see it here. Let's go back and look at that, because without this, we're really going to be lost. In this case, this is the input of function f. Why? Because it sits inside the function notation we have there. It is the input of function f. It also happens to be the output of function g. And so we would start with function g of x, find an answer, use that answer. It's kind of like what we did with the derivatives in a way. Find the answer and put that answer inside then the other function. The other way we could do that, anyone have a clue as to what we could do besides having f of g of x? Sure, we could have g of f of x. That means that I'm going to start with what function? Well, I'm going to start on the inside. Now listen to my terminology, because I use this a lot. I'm going to start on the inside function. I'm going to start with f of x, get an answer from that, and put that answer into function g. So g is the outside function. Kind of sits out there, doesn't it? And f of x is inside. It kind of sits inside. So my terminology is accurate when I use those words there. We have to understand this in order to do the chain rule. And so the whole section of 2.5 is the chain rule. Let's go on and let's see if we can't figure some more information out here. The chain rule says that y equals f of u. Now let's just look at that just for a moment. Y equals f of u. What is the input in this statement right there? Yeah, okay. U is the input. What's the output? Y. We could also say the output is f of u. Yeah, either one of those ways of saying it. So the input is u, the output is y, or f of u. It's a differentiable function. What does it mean that it's differentiable? Yeah, it has a derivative. You can find the derivative. The derivative exists. Any of those phrases would work. Okay, so this function, you can find a derivative for it, and it does exist. Okay, now we go over here. U equals g of x. Take a look at that. What's the input in this? X. What's the output? G of x or u. Now, in this problem, in this right here, this is what, an output, you say? But what was it over here? An input. It's an input. So I could say that since u represents g of x, here's my f of g of x. I can replace that with g of x. Okay, so here's an example where, this is an output. This is an output. And then yet I use that very same output as an input in another function. Well, let's go on and break this apart. That happens to also be a differentiable function. Okay, then y equals f of g of x. Well, how does that come about? Again, g of x is the input in function f. G of x is also represented by the letter u. And isn't that what I have over here? So we're kind of talking in circles, aren't we? In a way, it sounds like it to me, because everything's related, to relate to everything else. Okay, now, here's what we come up with. Remember that dy dx is another way of expressing a derivative. When I use the notation dy dx, what does that x represent? Input or output? You have to know this in order to be able to do these problems. So x represents input or output? Input. What does y represent? Output. So I'm going to find the derivative of y with respect to x. Now, which of these three highlighted expressions, can I represent with dy dx? And what I want you to focus on is what's the input and what's the output. Okay, is that the derivative notation for this? No, because the input up here is u, not x. Could it be this one? The input is x, but the output isn't y. What about down here? The input is x and the output is y. Okay, so dy dx is what we're going to find here. Well, what about dy du? Yeah, look at the input, look at the output. This derivative, let me get a different pen here. This derivative goes with that, because the input is u and the output is y. The input is u and the output is y. What about this one? Yeah. And again, all we're doing is focusing on what's the input and what's the output. Where do I find the input here? Where it's down here, the x. The output is u. The input is x. The output is u. And so this one is the one we're using to represent here. Okay, this is why we call it the chain rule. Notice that I've got two derivatives multiplied together. Now, again, as I said before, when I introduced this notation, the purist would have us say, don't think of these as a fraction. It's just notation, dy dx. And I'm thinking, no, it's not. There's a little more to it than that. There are differentials. Differential y divided by differential u divided by differential x. Now, differential u here represents the input of something, but up here represents the output. So they're not quite the same thing, but even those purists would say, well, if you look at that, those things can cancel. And what are you left with? Dy dx. What were we trying to find? dy dx. Okay, so the chain rule says if you want to find the derivative of a composite function, if you can break it apart into the two separate functions and take their individual derivatives, then just multiply them together. You get the derivative you want. A little more to it than that, but that's basically what we're doing here. Okay. Now, the other thing, though, is that there is another set of notation we could use, because we're used to seeing the f of x notation, and we're used to seeing f of g of x, and that's what I've got here. The derivative with respect to the input x of the composite f of g of x. Now, again, what does g of x represent in this f of g of x? G of x is the input expression. It is also, in and of itself, a function. And that function sits inside the notation for a function f. So it is the input, and let me switch colors here again. It is the input, and yet I'm going to call it not the input, but I'm going to think of it as the inside function. It is the input, its output becomes the input of function f, but we also then use the words inside, outside, because that function literally sits inside function f. Now over here, do we see, look at this piece right here. What does this say? Now what's that prime mark mean? Derivative of, so this is the derivative of the inside function. F prime of, so if g of x is the inside function, then f of whatever is the outside function. So what is this piece? Derivative of the outside function. Yeah. So if we think now not only of what is the input and what is the output, but what functions are we dealing with, and is one function inside the other? I've got other ways to make it a little clearer to you, so if you're a little fuzzy on this, just hang in there. I've got more ways to express this. But this is getting the notation to us. Okay. Let's see. What we're going to do, let's go to, I'm watching the clock here, let's go to this problem though. The first thing I want to do is, let's write it as the composition of two other functions. Because the key here is, can we see a composite function? If you can't see a composite function, it's a little harder to do this work. Okay, so if I'm going to look at this, let's call h of x, and we can let y equal h of x, and let's say that it's f of g of x. So we're going to identify f of x as the outside function, and we'll identify g of x then as the inside function. So go back to this. Now, here's the first key. If I told you x equals 3, what's the first thing you would take care of to come up with a value for y? What would you do, Hema? Yeah, I would first of all find 3 plus 2. Okay? That's the first thing I would do. So that makes g of x x plus 2. Okay? And when you think about that,